Good afternoon. My name is Gustave. I work in France in the Université Gustave, and I will talk about confined granular flows in this talk. This work has been done with 4 colleagues, Ricardo Artoni and Antonio Paul, also from the Université Gustave in France, and also Renaud Delannay and Alexandre Pallas from the Université of Confined in France. So as you know, granular materials are quite complex. And if you look at real-life granular materials, they can flow on complex topographies. If you look at their shape, it's quite complex. If you look at their size, you have large size distribution. But of course, as a physicist, when you saw such kind of real-life system, you say, well, it's too much complicated. So what we'll do is that we go back to much simpler systems. So, for example, if you want to study granular flows, you can carry out experiments in the sheet flows, like I'm sorry, I think that's a green light on the whiteboard. It's not very efficient.
It's a big stick over
there. There is a big stick.
Where is the big stick? Ah, perfect. Thank you. So, if you wanted to study granular flows, to try to understand what happens in real life, you often use very simple systems, very simple models, like sheet flows. Also, we have sheet flows, or simulations, or simulations. And of course, to avoid the complexity of the grain shapes and often of the grain size, you also use very simple grains, different spheres. Of course, you can change the material used for the sphere, but you often use isotropic grains. Okay. If you want if you want to add complexity about grain shapes, you can study elongated particles, which can be found in the nature. If you look at a system of logs, like here you have a flow of logs on a river, and such kind of elongated particles are quite easy to characterize because their shape is very simple. If you want to go deeper and deeper, if you want to study real logs, of course it is much more complicated because you have the shape is extremely complex and you need a lot of parametric methods to model it. So often what is done is that the shape is simplified by using polyhedra instead of real logs. Okay, so my talk is devoted to confined granular flows. So confined granular flows are quite ubiquitous in the industry and in nature. To illustrate this point, you have here natural granular flows in a canyon. And, so the flow is confined by the presence of the typical topography. And such kind of systems, so confined granular flows, are complex because due to the confinement, you may have correlations and non-local effects that are introduced by this confinement. And this confinement can be sidewall, can be the bottom, can be the top. And also it is interesting because if you look at systems which are very simple, like this one, it is just a gravity-driven flow between 2 sidewalls if you look at a certain kind of a system, you see that you have a very dense system here, where it does not move that much. And when you go towards the free surface, you have a very energetic flow and a very diffuse flow. So in a system, you both have a dense part and a diffuse part. So, and if you want to test the theories that are able to capture the solid behavior of a granular system and the liquid or gaseous behavior of the granular systems, some kind of experiments can be very useful. So it's a good system to test theory, and also if you want to use continuum modeling to study this system, you need to have boundary conditions at the sidewalls for this system. And so we can, with such kind of experiments, measure the velocity, the granular temperature at the sidewalls, and thus obtain boundary condition to feed continuum theories.
Really sorry, there's a bit of feedback from online.
Okay.
But this microphone is here, so if you can try and stand a bit closer to the microphone, because they can't hear you so well.
I have to stay here, right?
But yeah, because
Okay.
I think your back's to the screen, so.
Okay,
yeah,
okay.
terribly sorry.
No, it's okay. No
It's
problem.
long enough stick.
Yes. I have long arms, so it will be okay. Okay, so the aim of this talk is to present results about steady and fully developed confined granular flows. I will discuss the boundary conditions that we have found in such kind of a system. I will also study the influence of the geometry of the system by talking about two different geometries: a shear cell and a sheet flow. And a sheet flow system. And I will also talk about the influence of particle shape by using both spheres and elongated particles. So let me present you first the two geometries. So the first one is the confined shear flows, and the second one is the confined gravity-driven flows with an erodible base. So for both systems, we perform experiments and simulations, but the majority of the results that I will talk about comes from simulations. So for the first system, so it's a shear cell. So you have an inner cylinder, you have an outer cylinder, and you have a bottom and a top that are bumpy. The grains are between the two cylinders and between the top and the bottom. The bottom can move at a given velocity, and we applied a stress at the top of the system, as you can see on the sketch on my slide. So the parameters are the load, the shearing velocity, and also the confinement, because you can modify the properties of the system. The second geometry, the confined granular flows. So it's it is exactly the same thing that I show you before. So you have two sidewalls, and you have a gravity-driven flow between these two sidewalls. So the confinement is due to the presence of the sidewalls. And of course, in a such system, you have a free surface, which is not the case for the shear cell. And in this system, the angle of the flow depends on the input flow rate. It increases with the input flow rate. And so this is for the experiments and for the simulation. So we have the same geometries, but with the simulation. On your left, it's the shear cell. On your right is the sheet flow. So for the DM simulation, So we use periodic boundary condition in the main flow direction, and we have sidewalls at the side. We also have a bumpy bottom and top, and we use a slightly polydispersed grains. And the gap between sidewalls is set to 10 grain size. For the gravity driven flow on your right, so of course here we also have sidewalls. We set the flow angle and measure the input flow rate, and we can also modify the gap between sidewalls. And I think that's it. And the key parameter in this study is the friction coefficient between the grains and the sidewalls. So let's start with the first system, so with the shear cell system. So here I show you some videos extracted from the simulations. So you have 3 videos from left to right. On the left, you have a very low friction coefficient grain sidewalls. And when you go to the right, the friction coefficient increases. So what you observe is that the velocity profile, so that you can see on the right, on your right. So you have here the vertical position and the velocity. So what you can see is that with very low grain wall friction, you have a plug flow close to the bottom. Let me recall you that the bottom moves. And then you have a shear that is close to the top. It's the green curve on your right. And when you increase the friction coefficient, the shear localization completely changed from the top to the bottom. Okay, and then you have here a quasi-static zone in this system. So for the other geometry, which is the confined granular flow, which is the gravity driven flow, the velocity profile are reported here. And what you can see is that the shear is always localized at the surface, which is quite obvious, of course. And if you use frictionless walls, in fact, the wall system is a shear, but the concavity of the velocity profile change. So as you can see, between this system and the previous one, it is quite different. But if we look at the transverse velocity profile, so here I report the transverse velocity profile. So the sidewalls are on the left and on the right of each x-axis. And what we observe is that I report, for example, on the left, so the velocity profile in the creep zone and in the shear zone. And what we do see is that the relative transverse variation are more important in the creep zone. And it seems to be the same thing for the shear cell simulations, even if the variation are less important in that case. So another quantity of interest is granular temperature, so which is also the velocity fluctuations, which is exactly the same thing. And so when we report the velocity fluctuation, so on your left is for the sheet flow, on your right is for the shear cell, we observe completely different temperature profile when we compare the two geometries. If you look at the flow if you look at the gravity-driven flow on your left, so you can see that the temperature decrease when you go deeper and deeper, which means that the base is completely dissipative. In contrast, if you look at the shear cell, you see that the bottom is quite energetic because you have a bump. Yeah. And the curve that is different correspond to the case where you have a plug flow close to the bottom. So this is very, so the two systems for the temperature are extremely different. So if we want to sum up what is different between these two confined systems, so we have different shear localization, we have different transverse variation. So this means that the boundaries are very important, because here you have a free surface and here you do not have a free surface, and it changes everything. But if we look to other quantities, we can find some common properties. And one of them is, for example, if you look at the granular temperature, and if you report the granular temperature versus the shear rate, you can observe that you have a quite unique relation between these two quantities, which means that the square root of the temperature scales with the shear rate. So it is a power law, more or less. We may see some deviation from the power law, especially for the chute flow system. But with a good approximation, we have a power law with a power 3 divided by 4 in both cases. And also another common property is that if we look at the transverse granular profile, it's the same than before. So the center of the figure corresponds to the center of the cell, and the extremities correspond to the presence of the wall. So what we do observe is that depending on the zone where you are, if you are in the creeping zone or in the shearing zone, the side walls can be a source of temperature or a sink of temperature. So in the creeping zone in both the system, the temperature is minimum and maximum at the center, and it is the opposite in the case of a creeping zone. And such kind of properties is common to both systems. Okay. So one of the advantages of simulations is that we can measure what we want. And especially we can measure forces between grains, which is not obvious with experiments. So what we have done is that we have measured the effective sidewall friction. So let me first explain what I call effective sidewall friction and how we measure it. So here you have a simulation of a gravity-driven chute flow. And what we do, so I will have to show you something with a long stick, so I'll try to keep close to this guy. So what we do is that we create horizontal slabs, like the slab between the two gray lines. Yeah. And so we divide our system in different slabs. And for each slab, we measure the total stress normal to the sidewalls. And we also measure the shear stress at these sidewalls. So we measure at the stress sigma YY like that, and sigma XY, which corresponds to the shear stress. And we average, so in time and also for all the contacts in this slab. And if you do so, if you look at sigma xy, it can be zero because you have average, and if for some contacts the force is like this, and if for the other contacts the force is in the opposite, you will have zero. So we do that for both systems, for the shear cell and for the gravity-driven system. And we report the profile of this effective friction versus the depth in the system. So for the shear cell, the bottom is at 0 and the top is close to 40. And for the gravity-driven simulations, the free surface is close to 80. And so here we report the effective friction coefficient for different friction coefficients. And so let's start with the shear cell system. So if you remember, at a low friction coefficient, at low grain wall friction coefficient, you have a plug flow close to the bottom. And of course, in such a case, the effective friction coefficient is equal to the grain wall friction coefficient. But if you increase the friction coefficient, so you have no more, this plug flow, the shear is localized close to the bottom. And so what you observe is that you observe globally a decrease of the effective friction when you move towards the top of the cell. And if you look at shear cell, at the gravity-driven flow, which is here, so you observe a global weakening of the friction coefficient when you go deeper in the cell. So the effective friction coefficient is quite large, closer to the free surface, and then decrease when you go deeper and deeper. And so these properties, so the friction weakening, is common to the two systems. So as I told you, these results come from simulations, but actually, if you do not believe me, we measure it experimentally. And we also find a global decrease of the system. Of course, we only have 3 positions, but it is experiments. We have to move the force sensor, which is not that easy, but we also obtain such kind of results. So now, if you want to go back to a potential continuum description of granular flows, we have to find boundary condition, and we can say, can we find a boundary condition for the friction coefficient at the side walls? And so we start by looking at a given quantity, which is the streamwise heat velocity divided by the square root of the streamwise granular temperature. So we use this quantity because it is commonly used in kinetic theories when you want to decrease granular flows. You have different approaches. One of them is the kinetic theory, and they use the velocity divided by the square root of the temperature. So for the two geometries, we report the effective friction coefficient versus this quantity, and actually we find a scaling law which works reasonably, I would say. Of course, the points are the scattering of the curve is quite large, but at least we have a trend. Again, it is not perfect, but while it can probably be used as a boundary condition. But so what does that mean? That velocity fluctuation or granular temperature may play an important role to describe this boundary conditions. Okay, so all of so what I presented to you has been obtained with isotropic price with spheres, and of course it is very tempting to check if what we obtain also works with non-spherical particles. As I explained to you at the beginning of my talk, if you want to use spheres with complex shapes like real rocks, it is quite complicated. So what we have done is that we restrict ourselves to elongated particles, which are simpler to describe. So we model a flow of logs, and for this thing, so we also carry out experiments with elongated particles that you can see here, which are 3D printed, and also perform simulations with clumps of spheres. So we just create clumps of a sphere by overlapping spheres, and you can obtain elongated particle quite easily. So we use the same experimental systems than before for the shear cell, and we use also a simulation which are pretty similar to what we have done before, except that we use clumps of spheres instead of spheres. So let me show you two videos of this system. So the same things than before. So you have a bumpy top, a bumpy bottom. The bumpy bottom moves, and you create shear by moving the bumpy bottom. And you can clearly see a creep zone here and a shear zone close to the bottom, which is quite obvious. And so we perform exactly the same analysis than before. So we measure the effective friction coefficient at sidewalls in these systems. And in fact, if we try to report the effective friction coefficient, if we use the same scaling, so let me recall you that the scaling is the velocity divided by the square root of the temperature, it does not work. It does not work, so which means that the scaling that we obtained before is only valid for spheres. For elongated particles, the scaling that I reported here is not exactly the same, because on the x-axis you do not have the velocity divided by the square root of the temperature. You have a parameter kappa, which is the velocity at sidewalls divided by a times the square root of the average of the square angular velocity in the z direction. Quite complicated. So a is the size of the clumps. Okay, and in doing so, the scaling obtained is works well, and we can easily distinguish three parts. One at low kappa with no slip, you have a pure rolling because the rotation is important. A zone here between 0.1 and 10, where you both have sliding and rolling, and the last zone corresponds to the two pure sliding. And let me point out that it is quite important to write here so the rotation and not the fluctuation of the rotation, because if we look at the fluctuation of the rotation, which are indicated here, this quantity is extremely correlated to the temperature. And if we use to obtain a good scaling, we have to write the rotation velocity, not its fluctuation. So the scaling is quite different from the one we obtained with spheres. And of course, this scaling also works for spheres. So this corresponds to the yellow circles that you may not see on the whiteboard, but it also works. And we also try to use this scaling in case of the gravity-driven geometry. So this one, that is exactly the same that we have done before. And this corresponds to the red stars on your curve, and you can also see that these points also collapse on the master curve. So this is quite interesting because we have found one scaling for the effective friction at the side walls that works in two geometries and works for spheres and for elongated particles. And of course, the next step is to check if it works or not with more complex granular materials, which can be made of polyhedra. Okay. Okay, so let me conclude my talk. So what we have done is that we have studied confined granular flow with two geometries, shear cell and gravity-driven flows system. And what we have found that shear localization depends strongly on the sidewall friction, and also that the shear localization is different in those two systems, which is quite expected. But we have found also common properties with these two systems. So we have found global scaling of the temperature in the shear zone. We have shown that depending on the fact that where you are in the flow, if you are in the creeping zone or in the shearing zone, sidewalls can be like a temperature source or like a temperature sink. And we also demonstrate that the effective friction coefficient of a sidewalls decrease when you go towards the creeping zone. And we have shown that the velocity divided by the square root of the temperature, which is commonly used in the kinetic theory, can be used to scale our data, but only in the case of spheres. If we use elongated particle, we have to use the other scaling, which use the rotational velocity of the grains. So the go-home message is that so interfaces have to be taken into account because you have to know what are the boundary conditions that you have to use in your work. And this is probably especially true for industrial application where you often have confined granular flows. Thank you very much.